In this video, we're going to look at one last gas law, and it's something that is extremely relevant, especially in certain kinds of laboratory situations. It's called Dalton's Law of Partial Pressures. And what Dalton's Law says is that when we have a mixture of gases, the total pressure of the mixture of gases can be broken down into individual components, that is, individual partial pressures of each gas, based upon the amount of gas that is present for each one. So if I look at the total pressure, if I'm measuring atmospheric pressure, the pressure that I measure is equal to the individual pressure of the nitrogen, plus the individual pressure of the oxygen, plus the individual pressure of the carbon dioxide, plus the individual pressures of all of the other trace gases that are available in the atmosphere. If I add all of those together, that's what comes off as atmospheric pressure. Now, if I want to know any of the individual pressures along the way, all I have to do is take that total pressure, the thing that we measured, and multiply it by the abundance, the mole fraction of the component that I'm interested in. And that would give me the individual pressure associated with whatever the substance is. Now, this equation should look familiar to you because it's a variant on Raoult's law, vapor pressure lowering. Mole fraction times pressure gives us the pressure of a component in this case, and Raoult's law told us how much our vapor pressure had decreased. Now, where this is particularly useful is in reactions where we collect gases over water. So in this particular reaction, we've got potassium chlorate, and we're lighting the heck out of it on this Bunsen burner. And what happens is, as it does, we get potassium chloride and oxygen gas. And the oxygen gas comes through the bubbler here, and we collect it over water into this jar. Now, inside of this jar, in the airspace, we do have the oxygen that was generated by the reaction, but we also have to recognize that water is volatile to some degree. And so there's water vapor in this area as well. And so not only do I have oxygen, I also have to have water vapor in here as well. And so if I measure the pressure inside of this bottle, which I can assume is pretty close to atmospheric pressure, I can't really know how much oxygen is here until I know how much water vapor is there. And that's where those vapor pressure values and those tables of values can come in handy. And so let's take a look at an example of a problem like this. We have a sample of potassium chlorate that is heated and decomposing to form oxygen gas. The gas is collected via water displacement at 25 degrees Celsius. Total volume of the collected gas is 329 milliliters. Pressure is 744 torr. How many moles of oxygen are formed? Well, it'd be really easy to look at this and say, oh, well, I've got a pressure, I've got a temperature, I've got a volume. Let's plug that into the ideal gas law. Problem is, we know that some of this pressure here is associated with water. We just have to figure out how much. And that's where that table of values comes in. And if I look up on the table of values, I see that the vapor pressure of water at 25 Celsius is 23.8 torr. So before I can move on into figuring out and solving the rest of the problem, I have to take this pressure issue into consideration. And this is where Dalton's law comes in. Dalton's law says that the total volume or total pressure is equal to the sum of the individual pressures, which means if I know the total and I know one of the pressures inside, I can subtract and come up with the pressure for just the oxygen. So 720 torr, that's the pressure of the oxygen. Now, I just need to solve the rest of the problem. N is equal to PV over RT. My P is 720 torr. My V is 0.329 liters. Again, remember, I turn those milliliters into liters before I start using the ideal gas law. Since I'm in torr, 62.36 liter torr per mole Kelvin is my gas constant, and T, 25 Celsius, is 298 K. I do a little quick check around. Okay, liters cancel, torr cancel, Kelvin cancel. I'm left with just moles. And 720 times 0.329 divided by 62.36 divided by 298 to 3 significant figures, I get 0.0127 moles of oxygen were produced by this reaction. And with that, going back to what we saw in the last video, now we could take that number of moles of oxygen, we could use it to figure out how much potassium chlorate was there, how much potassium chloride is the byproduct left over. Lots of different directions that we can go with it here. But that's one of the ways that we can use Dalton's law of partial pressures in a real laboratory kind of situation. I want to end our discussion of gases talking not about a gas law, but about some assumptions we've been making along the way. One of the reasons why we call it the ideal gas law is because it is based upon the fact that the gases that we are studying are behaving what we call ideally. And what that means is they're behaving according to the kinetic molecular theory. The problem is the kinetic molecular theory doesn't always predict real behavior. And so when we go away from ideal behavior, we get into a phenomenon or a classification, however you want to call it, where we describe the gases not as ideal, but as real gases. And there are two particular scenarios where real gas behavior must be accounted for. And they have to do with fundamental assumptions made by the kinetic molecular theory. The two conditions are when we are at high pressure, that is, our volume has been decreased considerably, and when we're at low temperature. And the reason why low in temperature is important is the kinetic energy is going to be decreased significantly. There's a chance we might have a little bit of interaction taking place between the molecules. We actually get some intermolecular forces going on there. And that flies directly in the face of two of those fundamental assumptions. The first fundamental assumption is that when the container is gigantic compared to the size of the gas particles, we can generally ignore the gas particles having volume. When that's not true, then we have to account for it. We have to account for the space that the molecules take up, and that's going to be an adjustment that we have to make. And the last assumption, dealing with those lack of attractive forces, we know that when the molecules are moving around really, really fast, they might collide with one another, but they're not going to touch each other very much at all. And so what we see is that ideal behavior tends to be valid at normal kinds of conditions like STP. But as soon as we get to higher pressures, these real properties take over. And these real properties can have some pretty significant impacts on the overall way that we use our gas laws. Now, luckily, some people that have come before us have helped us to correct for those deviations from ideal behavior. And that leads us to something called the van der Waals equation. Now, in terms of the van der Waals equation, I wouldn't get caught up in actually memorizing this equation. I'm not going to ask you about it. What I want you to understand, though, is that when we have deviations from ideal behavior, this is how we account for them. And we can see that there are two correction factors. There's a pressure correction and there's a volume correction. The pressure correction accounts for the attractive forces. So these are the forces associated with the attraction. The intermolecular forces that can occur. And then this correction here is everything about the volume, size correction. And so the van der Waals equation allows us to account for those two things. And the values of A and B are unique to every single molecule. So every single molecule has its own values of A and B, these van der Waals constants. But what the van der Waals equation allows us to do is that if we apply these corrections, the overall impact of the ideal gas law, we can still use it. And these aren't terribly difficult corrections and mathematical manipulations to make. They're not bad at all, really. But this allows us to broaden the scope of the ideal gas law to gases that are not exactly behaving ideally. So this is the last video in our Chapter 10 series here. We'll be moving on next to talking about nuclear equations and reactions in Chapter 21, and that'll actually close out the semester for us. So until then, have a good day.